Okay, so good morning, everyone. So thank you for coming to the lectures. So today is the third lectures by Vera in the series of MoCaO Lectures for 2024. And so today Vera is going to talk about convexity in general vector spaces. Okay, over to you, Vera.
Thank you very much, Tom. Thank you very much, everybody, for joining. So yeah, again, it's the last lecture by me, but not the last lecture in the series. There will be much better and more exciting lectures on Thursday and Friday by Isabel and Bruno. So today I will talk about convexity in general vector spaces, and I selected some interesting, fun things that are classic or very classic about convex sets and general vector spaces. So I just want to give, to share with everybody the flavor of infinite dimensional spaces and why they're so interesting and exciting to work with, and why convexity is a really interesting thing in the context of infinite dimensional spaces. So I'll go over some very classic examples that demonstrate the differences between general vector spaces, how convexity works in infinite dimensional spaces and in finite dimensional spaces. So it will be mostly about contrasts, how things are completely different. And I haven't worked in infinite dimensional spaces for a long time. In fact, I only started working with this with Rainier, who is here, my collaborator. So we wrote a couple of papers on this. But I find it absolutely fascinating. So please, again, feel free to comment, add things, ask questions during the lecture in the chat, or just turn on the camera and microphone and speak. All right. So also, I mean, we can think about why do we want convexity, or why do we want to study general vector spaces, especially for optimization? Obviously, because some optimization problems are infinite dimensional. Like the really hot topic these days, the optimal mass transfer, right? That's the Kantor-Rich-Monge problems. They are convex problems in infinite dimensional spaces. So there's, of course, other problems. There's a lot of problems that are convex and not finite dimensional, optimal control problems, whatnot. I think that studying convexity in general spaces tells you a lot about how the structure, the particular mathematical structure affects different properties, right? So you see how what you're doing comes from the linear space, what you're doing comes from topology, and so on. So it enriches your thinking about convexity, about optimization, and so on. And also because some problems that are finite dimensional, they actually behave almost like an infinite dimensional problem when the dimension is very large, right? Like what happens with the modern big data and optimization methods for huge problems, right? So they can actually be very close to infinite dimensional problems. Okay, so let's talk about something very basic. I didn't mention convexity before. Sorry, I didn't mention separation before, because I wanted to talk about separation in the context of general vector spaces. So let's remind ourselves the very basic idea of separation. So if we have two closed convex sets, or just two convex sets, actually, two disjoint convex sets in a finite dimensional space, then we can always separate them by a non-trivial hyperplane, right? There is some linear function that we can represent as an inner product or an X transpose V, something like this, right? Something more basic. We can choose the standard inner product on Rn. So basically, it means that you can, for any two convex sets, you can draw a hyperplane, you can place a hyperplane between them. So it doesn't mean that you will always have strict separation. It can actually happen that both convex sets will be inside this hyperplane, or you may only have one of them kind of strictly outside in a sense, right? There will be some relative interior point outside of this hyperplane. But the most important thing is that any two convex sets I take, I can always split them, right, with a hyperplane. I can always draw a hyperplane between them. So of course it can happen that, like I said, B is like this, set A is like that. So maybe I wouldn't be able to separate them strictly in a sense, but I can always find a hyperplane. And here's an example that I'm going to build on in infinite dimensions. So for example, think about this funny set that consists of all points with the largest non-zero coordinate positive, right? So I take my point, I look at its coordinates, x1, x2, x3, and so on. And with the largest index that is non-zero should be positive, right? So there's some examples here. So for instance, in the plane, right, I take, if the point has 0, x2 coordinate, then I only put the points with positive x1 coordinate in the set. 0 is kind of could be in the set or outside of the set, depends on how you interpret this, right? So, and then I will take the complement of that. So the complement of that is a convex set, and I can separate them with a line here, with a hyperplane. I can do it in 3 dimensions, right? So I look at this picture, it's exactly the same, right? So if the point has 0, x2, and x3 coordinates, it's only the positive side of x1. Then if it has the 0, x3 coordinate, I take the same 2-dimensional set and I can build up and up and up. And again, this set and its complement can be separated by a plane, or in higher dimensions by a hyperplane. So if I do this in an infinite dimensional setting, I'm going to hit a problem. And let's look at how this happens. So now I'm going to switch to real vector spaces. So I'm not going to have any topology on those spaces as yet. So it's just a real vector space. So we just have the linear structure. Think about the space of continuous functions, space of polynomials. Just as long as the space is real, right? You can add, multiply by constants, and so on. But we don't talk about closure or interiors or open sets and closed sets as yet. We only have a linear space. And amazingly, just with that structure, a lot of very interesting things can already happen in infinite dimensional spaces. And we can look at a lot of things related to the structure of convex sets, right? Without any topology, nothing like that. So we have this lemma by Stone, lemma Stone. It actually comes from Holmes. There's a really nice book by Holmes on analysis in infinite dimensional spaces. Don't remember what exactly it's called. It's a classic textbook from 1970s. And suppose that in a general vector space, we have 2 disjoint convex subsets. Then the only thing we can say is that there exist complementary convex sets, C and D, in this space, such that one of those convex subspaces will be in one of these complementary convex sets and the other one will be in the other, right? So when we are in n-dimensional space, right, we'll take A and B and then separate them with a hyperplane. And of course, one of those complementary convex sets will be one side of the hyperplane, maybe with also some separation within the hyperplane, and the second one will be the other one. But it doesn't happen like this. It doesn't always happen like this in infinite dimensional spaces. And in fact, every infinite dimensional space will have a convex set or a pair of convex sets that cannot be separated by a hyperplane. And this is a very classic example. I don't like this example because this example is non-constructive. However, I don't have a better one, right, to demonstrate this. So we look at this previous example that we had in finite dimensions, right? So we think about the set, that it's a convex set of all points now in the infinite dimensional space that have the maximal coordinate positive. So in any vector space, and this comes from the axiom of choice and all those results, right, that are very non-constructive. So in any vector space, there's a basis. In any real vector space, there's a basis. So any point in this vector space can be represented as a finite linear combination of elements from this basis, right? So it's a linearly independent system that spans the whole space. I can order this basis not as in 1, 2, 3, 4, 5, right? I can order it in the sense that if I pick any 2 elements from this basis, that for an infinite dimensional space will be infinite, then I can compare them, like, so, or I will have the minimal element, right? So I can compare which kind of index of this basic element is lower, which one is higher. So now, why it's impossible to separate, it's also a convex set. It's not easy, it's not difficult to see that it's a convex set. Why is it impossible to separate something like this from its complement that is also convex? So because suppose that we have a linear function from our space, right, to just the real numbers. And I'm talking about very basic things on general vector spaces. So if you're thinking about Hahn-Banach theorem and topological vector spaces, this setting is a lot easier than that. There's no Hahn-Banach separation theorem. It's just a linear space. We don't talk about continuous linear functions, for example. There's no continuity because there's no topology. So suppose that we have a linear function and it can separate the set C from X without C. And also there's this 0, but I can put it in C or X without C, a complement of C. So suppose that we can separate them, right? So suppose that that L of X will be non-negative if X is in C, and L of X will be non-positive if X is not in C. So now let's take any basic element, right? So, and then the thing about Hamel basis that also is, for somebody who is a very constructive person who works in maybe even applied optimization, it's something that doesn't make a lot of sense because given a linear vector space, we can't actually like write it down. We know it exists, but we can't present Hamel basis. We know that it's there, right? So now suppose that I have a basic element. Oh, thank you so much, David, for actually posting the reference. It's a great book. So now suppose I have a basic element from a basis. Take an element of the basis. Let E be a basic element. So now also we assume that the basis that we have doesn't have a maximal element. So this is not a base, it's not a maximal element. Choose another one that is larger. So then let F be some larger. So it's just like a higher coordinate, right? So it's like if E was in the finite dimensional kind of analogy, if E was E2, then F would be maybe E3 or E4 and so on. So you can see, right, that in finite dimensions, we will run out of the larger elements, but in this case, we won't. So then if I look at L of E, because it's the E itself, it has the positive coordinate, right? It's 1 multiplied by E. So this should be greater or equal to 0. Now, if we take this F and add to E with some negative scalar, then what we're going to have for say alpha less than 0, we're going to have L of E plus alpha F. So this guy has negative largest coordinate. So this should be less or equal to 0 because we have separation. So this guy is not in C. But then if I look at this linear function, it is a linear function. So L of E plus alpha F is L of E plus alpha L of F. So, well, this is negative, fair enough. This is non-negative. So now this is less or equal to 0, but this is less or equal to 0 for any alpha, right? So if I let alpha go to 0, negative, but going to 0, then I have to have L of E less or equal to 0, right? So for on any basic element, the value of this functional is 0. So it's just a trivial functional, right? It's just 0. So we can't separate these two sets by a non-trivial linear function. So it's a very basic example because it's something that can be used to characterize infinite dimensional spaces. And any questions on this or comments? There are some people in the audience, like David, who recommended this book, who knows this infinitely better than me. So David or anybody who knows more and maybe can see that I'm missing something or making mistakes, please just use the chat or say things. Yeah, just start talking. Okay, so it's impossible to separate convex sets in infinite dimensional spaces sometimes. And in fact, it always happens. So we can define, again, because we don't have topology, we can define linear closure of a convex set by doing the following things. So we don't have topology in our space, but we have topology on real lines because it's a real vector space, right? So if I take a span of a vector, within that span, I can do everything that I can do on the real line. So we can define this weak closure like this. If I take any, right, I take any convex set. Let's think finite dimensionally, this convex set is not closed, right? So say the boundary is not part of this convex set. And then what I do, I take all intervals inside this convex set. I take an interval like this, right? And it may be open as a subset of a real line, but I can also close it again within that, right, real line, because I have a topology of the real line. So I can take all line segments and close them. And actually in the finite dimensional space, that will give me the closure of my convex set. So there is nothing else in the closure of the convex set. I just close all line segments and that gives me the closure, right? So if my convex set was in Rn, then I will just get the topological closure of my convex set. However, in infinite dimensional spaces, it doesn't work like this. In fact, if we can find some convex set such that this linear closure gives us the whole space, and think about finite dimensions, how is it even possible to have a finite dimensional convex set such that this linear closure is the whole space, right? So it's a characterization of a finite dimensional space, infinite dimensional space. The linear space is infinite dimensional if and only if it contains a proper convex ubiquitous subset. So any infinite dimensional space will contain a convex set such that it doesn't coincide with the whole space, so it's proper. And also, if I take this linear closure of the set, it will fill the whole space. And in fact, that's exactly that example that I was talking about, right? The example that gives us non-separation between two convex sets in infinite dimensional spaces. So if I want to prove this theorem, of course, I'm not going to give all details. So the first thing I will want to do is to say that, well, in finite dimensions, it's impossible because actually I can use the separation theorem. Right? So if there's a point outside of my convex set, I can separate that point from the convex set, and everything that is in the half space that doesn't correspond to where the set is living, well, it's not in the closure of the set. So obviously I can't have a ubiquitous convex set like this. But in infinite dimensional space, I can use exactly the same example, right? So remember, I can take this basis infinite basis, order it in such a way that there's no maximal element. And then what I can do, I can show that that set is ubiquitous. Yeah, so let's quickly show that set is ubiquitous. So, right, so largest coordinate is positive. So I take some point, right, in my set C. And let's say X is some alpha I, EI, where alpha I and EI are some basic elements. And well, let me write it like this. So it's some index set, and this representation is finite, of course. So I can pick something that is, wait, so yeah, I need to show, sorry, I need to show it's ubiquitous. So let's take X in this whole space. Let's write the representation of X. So if the last element here has a positive coordinate, right? So last alpha I is positive, then X is in C. And of course, it can be either positive or negative because right, it's with 0, it doesn't feature in this representation. Alpha I is negative. Then we can take some higher element from the basis. F, right? And then we take Y that equals to X plus TF and with positive T, right? So then this will be in C. And of course, as C goes to 0, we'll get X. So even though X is not in C, we are within the same line, right? So this line segment from X to Y will be in C. And so X, Y will be in the closure of C, linear closure of C. And so because we picked any X and X, and we have put it in the linear closure, right? From here, we can deduce that the linear closure of C is the whole space. So I'm not really comfortable with these examples, but there will be some other examples of similar things happening that are more constructive, because this is not constructive. I can't write down this basis, right? It's just existence from the axiom of choice. Okay, so now another thing about this really cool thing, linear closure, is that, so remember how I said that in finite dimensions, I take this linear closure and I actually take, and that is actually the closure of my convex set, right? In just the basic topology of Rn. If I do it in an infinite dimensional space, it may happen that then the closure of this closure is different, and the closure of the closure of the closure is different, and like, right, it can happen many times. And there is a fascinating result by fascinating example by Nicodim that shows that it can happen no matter how many iterations you take. And it's even more fascinating because what you can do, you can define this linear closure of any order, right? So you take the convex set, define linear closure as taking closures of all line segments in the set. That will be like the first iteration, right? Then you define the next iteration by taking one more, doing it one more time, and so on. So that way you can define it any finite number of times. But you can go further. So you can actually define this linear closure for any ordinal number. So if you take some ordinal number such that the previous number exists, right, then you define it in the same way. It's the previous one, and you take the linear closure. If you get the linear limit ordinal, then you define it as the union of all preceding linear closures, right? And yeah, the point at which the linear closure of the convex set of this particular order always coincides with the linear closure of the next order is when you're using the first uncountable ordinal. And there's an example by Nikodym that tells you that if you take any ordinal number that is less than the first uncountable ordinal number, then you can construct an explicit example for which the linear closure of this order does not coincide with the order of this plus one. So this is, I think, really fascinating, because that is something that is unimaginable, right? If you work on infinite dimensional spaces. And there's a lot of really interesting examples and really interesting work done in the 1950s. Okay, so there's no corrections or additions. So I talked a little bit about closure. So this is algebraic closure in a vector space that has no topology, right? I can take an algebraic closure of a convex set, and already interesting things happen. It doesn't coincide with the next order of the closure. You can also define kind of linearly closed sets. So you just say that the convex set is linearly closed, that if you take any line segment inside the set, then the endpoints are in the set, right? So that will be like the largest closure you can take. And eventually, I think once you are here, right? Once you are in this setting, then that will be actually somebody wanted to clean my office, sorry. So that will be actually the closure, this largest closure of this convex set. Okay, so that's about closures, as much as we can do just with linear structure. And now let's talk about interiors. So remember, in finite dimensions, we have the idea of the relative interior. In infinite dimensional spaces, things are more complicated than just having relative interiors, because, relative interiors of convex sets can be defined in different ways. So when I was talking about relative interiors, I defined the relative interior as the points in the set such that the minimal phase for those points coincides with the set. I can also define the relative interior as the interior of my convex set within the smallest affine subspace that contains the set, right? So I take a disk, for example. It can live in high dimensional space, three-dimensional space, whatnot. I take the smallest affine subspace that contains it, which will be a plane, right, in this example. And then, of course, within that plane, the relative interior will be actually the interior of that set, the topological interior of that set. If I'm in a general linear vector space, don't have topology, I cannot talk about topological interiors like this. Also, things get a little bit complicated with taking the smallest affine hulls, because the smallest affine hull may not be a closed affine subspace. And yeah, so we'll get all sorts of issues with topology there. So, but the particular generalization that is based on minimal phases, or a generalization that is based on how we did take any point in the convex set, draw a line through X, and it should be able to continue that line within C, right? It should find some point beyond X. Those definitions work. But in infinite dimensions, this notion is called the intrinsic core. And in fact, that causes some confusion, because there's a lot of people working with these notions in different fields, not necessarily in optimization, not necessarily even in convexity, because these things can be defined for general sets as well. And there's a lot of different names for the same thing. So sometimes it's difficult to even find papers that are very recent that are on the same topic. Okay, so we have the definition of the intrinsic core. This definition coincides with the definition of the relative interior, but not with the other equivalent definitions of relative interior. And immediately we hit a problem. The problem is that intrinsic cores can be empty. So remember, in infinite dimensions, working with relative interiors and minimal faces is really convenient and useful because those things are always non-empty. You always have an interior point in your set. You can check like later constraints, constraint qualifications and things like this because you know what's the interior. In infinite dimensions, it may happen that intrinsic core is empty, and it happens not only for freaky examples that are non-constructive. So you wouldn't be surprised by now, right? If that I say that in the previous example with Hamel basis and ordered basis, ordered Hamel basis, the intrinsic core of that convex set is empty. But if I work on more practical optimization problems, I will say I'm never going to use that example in applications. So I'm probably safe, but I'm not, because this thing is empty even for something very concrete. So there's a very cute example by Borman and Goebel about a subset of the Hilbert space for which the intrinsic core is empty. So this subset is in L2 space. So if you don't work with infinite dimensional spaces, right, L2 space, the sequence space, it's really one of the simplest generalizations of Rn. So you just have a space of sequences, right? So any point in L2, it's just basically an infinite list of coordinates, right? And we want to make sure, so it's only in here if the sum of xi squared is less than infinity. So we take what basically would be, in this case, the unit ball. And in that unit ball, we'll only take points with non-negative coordinates, right? So we want this, the sum of xi squared, this series to be less or equal than 1. And we want every coordinate to be non-negative. So this set has the empty intrinsic core. And the explanation given in that paper, where this example is, from which this example comes from, is very interesting, because what is done to show that intrinsic core is empty is to demonstrate that for every point in this convex set, every sequence like this, there exists another sequence that, in a sense, in a certain sense, converges slower than that original sequence. So if I have some, so first of all, if I take some point in C, and let's say this point only has a finite number of non-zero coordinates, finite number, non-zero. Well, then it's definitely not in the intrinsic core, right? Because then I take some y that will be equal to something like some tx, and then plus a higher, right, so some higher element, or something like, let's say, I just want to use something small, let's say mu e I, right? That will be a basic element that is not participating in X. And then, of course, if I try to then draw a line from Y to X and continue, I wouldn't be able to, because anything here, if this is positive and this is positive, anything here will have negative coordinate like this, right? Because EI is not participating in X, right? So xi is 0. So that's already not in the intrinsic core. But if we take something that is infinite, right? So let's say X has infinitely many positive coordinates. So if X has infinitely many positive coordinates, then I can construct my sequence Y right? So I can think about my X as some kind of a graph. Some people may not find this useful. Some people may find it a bit obvious, right? So this will be my xi, so x1, x2, and so on, x3. Right, so I have infinitely many of them that have a positive coordinate. So of course, xi by itself goes to 0, right, as I goes to infinity. So I can just keep collecting those positive xi's, and then I will let my y to be mostly 0. Right, so maybe I will have 0 here, here, and here. But eventually, I will make it a lot larger than xi. So we'll put it here. Right, so that will be my y, whatever, yk. And then I will continue like this. And then I can make sure, because xi's are going to 0, but there's infinitely many of them that are positive, I can make sure that the norm of y is actually not larger than the norm of x, right? So it's almost like I will be adding those xi's as long as I want. And then eventually the sum will be greater than the next xi. So I will put y here, but the difference will be getting bigger and bigger. So it's like a hand-wavy explanation of what happens with those slow convergent sequences. But in fact, what we have is that for any x, and for any, let's say, delta, that will bound the norm of y, there exists some y. So the norm will be less or equal than delta. We can also say that each y is positive, and such that for any epsilon, there exists some index I, such that xi will be less than epsilon yi. And here in this example, xi's are positive or negative, but we can also put it here like this. So then the same horrible thing will happen. So now I wouldn't be able to put anything beyond x. So if I connect y and x, right, because I will be looking at the ith coordinates of this point z, right? So I will have z equals to, say, x plus some t, x minus y, and then I will bound this particular coordinate that I have. Right? So I want this to be in the set C for any coordinate. So I will bound it by this. For any epsilon I pick, right? I can find I for which this works. So I will have this as less than epsilon yi plus t, and then epsilon yi minus yi. So of course, right, no matter how small is my t, I will always find an epsilon that will beat it, right? And that will make this z less than 0, right? No matter what t I pick. So I can't actually continue beyond x. And so the set has an empty intrinsic core, right? No matter what point on the set I pick, there will be always some y that is so bad that I can't draw a line through x and continue beyond x. And of course, it won't happen if I don't have this constraint. If I just take the ball, everything is going to be fine, right? I can take, yeah, I will be able to, I think, find the point. So even for this very simple example, the definition of relative interior, one of the definitions, doesn't work, right? I get the empty intrinsic core, or empty what would be the interior of this cone, of the set. However, some things still work. So for instance, we have the decomposition into intrinsic cores. And this is the same as the decomposition into relative interiors of faces. So certain things still work. So if I take a point from my convex set C, then there will be a unique minimal face. So I have minimal face defined in exactly the same way, intersection of all faces that contain X. And also, the intrinsic core of that minimal face is going to be non-empty. Right? So it's not too bad. And I still have a disjoint decomposition into intrinsic cores of faces. But there is something else in that set. And this decomposition doesn't give you this neat kind of hierarchical structure like in finite dimensions, right? So like if I take a polyhedral set, I will start a polytop. I will start with vertices and edges and so on. It's a little unclear what are the possibilities for the structure, right? So I would say that we don't know a lot about the geometry of faces that have empty intrinsic cores. We don't know how they fit with the rest of the faces, with the minimal faces that do have non-empty intrinsic cores. So some is known, and somehow there have been a lot of papers recently on these things. So these things are getting popular again. Yeah, but I don't think much is known unless we miss some papers from the 50s, because in the 50s a lot has been done already on that. Okay, so cool. So let's look at another thing. I think it's also a basic thing, and I think I have been advertising it to rest of people, because there's a difference between the way chains of faces work in finite dimensions and the way chains of faces work in infinite dimensions. I think that is something that I expect Bruno will be talking about in his lecture when he mentions facial reduction, that for a finite dimensional convex set, there is finite chains of faces. Why is this important? This is important because, exactly for the reason of facial reduction. So suppose that I have a convex problem. I look at the feasible region, and in that feasible region, I have some kind of a convex constraint that is nonlinear, like a cone for conic programming. And then I have a linear constraint, and I really want that linear constraint to cut my cone through the interior. And if it doesn't happen, then I will be trying to look at the face of my convex set where this linear space lives, right? Such that I can get an interior intersection. So because in finite dimensions, chains of faces are finite, right? So a chain is just, in this case, a sequence of inclusions, right? So I have a bunch of faces such that for every two faces, right, in that kind of collection, I can tell which face is the subface of the other, right? So that's a chain. So I cannot pick two different vertices because they're not related, right? I can't say that one is the subset of the other, but in this case, in this picture, every one of them is a subset of the other. So of course, in infinite dimensions, we don't expect the chains to be finite, but it's even more interesting, maybe not that interesting after looking at those examples that are pretty weird, that the convex sets can have, even in some very nice spaces like L2, they can have faces that are uncountable. So I can have a chain of faces that I can't line up like this, even in an uncountable way. And the way to construct it is to take some set. We take the set that in some references is called Hilbert cube. So this example comes from a paper with Rainier, but it's not like a super new example that nobody knew about. It's kind of classic, but we didn't have a specific reference for it. So it's like a generalization of a square of a cube, right? But infinite dimensional. So I take something like this, but I add more dimensions, right? It's like a hypercube, but I imagine more and more dimensions, so it becomes infinite. So let's say one here, one depending on where my x and y is, right? So maybe this is x1, x2. I will have put 0 here. I'm messing up this picture. So 2. Put 1 here, 1 and 2 here, 1 and 3 here, and so on, right? So of course, if I was in finite dimensions, then faces are very simple things. I will again have vertices and edges and facets and things like this. But in this case, I can take any subsets of natural numbers, right? So I can take, this is just a power set of natural numbers, subset of 1, 2, and so on. So if I take any subset like this, I can identify a phase of my convex set with it. So I simply take, it's like a direct sum or direct product, what some people will call it. I just take the coordinates of those points that comprise the faces. They will be 0 if for the index that is not in the subset, and there will be the entire line segment on which the faces are built if the index is in that set, right? So like here, if I take, say, what should I take? Maybe 1, 3, right? So then my face will be, I will take this whole thing here. I will skip x2, and I will take everything that corresponds to x3. So this face will be something like this. And I can do it in infinite dimensions, right? Pick an index, build a face. So, but because in that case, I can have a chain of subsets of natural numbers that is uncountable. I can have chains of faces that are uncountable, because if one selection, like C here, right, is a subset of the other, then faces will also be subsets of one another, quite clear from the definition. So I can have uncountable chains of faces of convex sets, even this very simple example. Right, so it's another thing that doesn't fully work in infinite dimensions, so maybe a thing that is more interesting in infinite dimensions. All right, so let's talk a little bit about the Arden topology, and then I hope that I will still have time to mention something interesting about the convergence of projection methods, or very basic projection method, the method of alternating projections. So there are ways to fix it. Not to fix it, but to make sure that we get something that is kind of like an interior that is non-empty. So once we have a topological vector space, we can define different notions that generalize relative interior in finite dimensions. Of course, in finite dimensions, everything will be the same. All those definitions will be the same. There are quite a few notions, but the most well-used is quasi-relative interior. And when Rainier and I were working on our paper, we were told by a referee that, contrary to what we thought that was actually introduced first by Bowen and Lewis in 1992. It was actually first introduced by Sir Antonelli in 1971 under a different name. In any case, what you do, you take one of the equivalent definitions of the intrinsic core. For example, in this case, I can characterize quite easily the intrinsic core as all points in my set C such that the conic hull C minus X is a linear subspace. Right, so again, let's take our triangle. I take a point from here. So C minus X, well, it's the same as just assuming that this point X is 0. I take the conic hull of what I have here, right? And it's actually the whole space. So that means that this point is inside the intrinsic core, right? If I take a lower dimensional convex set, again, if I take something here, right, I take the conic hull, then it will be a linear subspace. So this point is in the intrinsic core. If I take a point on the boundary, then it's not going to be a linear subspace. So it's just one of the equivalent characterizations. So for quasi-relative interior, we take the closure because we have topology, so we can take closures. But take a closure of that and demand that it's a linear subspace. And amazingly, this set is non-empty in a lot of settings. Also with Rainier, we recently introduced something that we call phase relative interior. So instead of taking closure in this definition, we take a closure in this basic definition of the intrinsic core. So we require that our convex set should be the subset of the closure of the minimal phase. And that also generates something that can serve as the interior and is non-empty in a very general setting. So if we take a non-empty convex subset of a separable Banach space, it will have non-empty quasi-relative interior and non-empty phase relative interiors. So the geometry is kind of, I mean, to me, it's a little bit less fascinating, but it's a very useful notion. So there's a lot of papers that use quasi-relative interior. for optimality conditions and for all sorts of things in infinite dimensional optimization. We also have sandwich results, so different notions are subsets of one another. There's examples that show that all those things are different. So of course, intrinsic core can be empty, quasi-relative interior can be non-empty, and so on. And I wanted to put this question out there that is asking if there is a convex subset in some topological space, X, such that the face relative interior is empty, but the quasi-relative interior is not. So maybe for people who are not that interested in infinite dimensional spaces, it's a bit too far, right, from your interest. But for somebody who likes this kind of thing, I think it's an interesting problem, right, to see how different generalizations of intrinsic core are related and if they are non-empty under the same condition. Okay, so I think I still have a few minutes, and I'm going to go through some, it's again very classical results about projection, because I wanted to mention projection methods. And in fact, projection methods, when we write papers on projection methods, we quite often use Hilbert spaces, because Hilbert spaces are a really great setting for working with projections. So a Hilbert space is a space with an inner product that is complete. So, for example, L2 is a Hilbert space, right, in which inner product is defined very similarly to the inner product on Rn, right? So if I take the space L2 that I was talking about, then I will just have xx like this, sorry, xy like this, after sum of xi, yi, right? And the norm on a Hilbert space is consistent with the inner product. So the norm of x will be this, right? So if we talk about, so I haven't talked about projections yet, but in finite dimensional spaces, most of you will know that projections are unique on closed convex sets, right? That's why we can actually have projection method. And it's the same in Hilbert spaces. It's not the same in general, right? So there's a very simple example of, I can take my space R2, and projection means that I want to find a point in my convex set that is the closest to a given point, right? So here, for example, projection of 0 onto some linear subspace is the set of points in that linear subspace that have the smallest distance, right, to 0. So if I don't make a lot of assumptions on how my topology and how my inner product and how my norms are defined, then I can get ridiculous things when projections are non-unique, right? So for example, in this case, I have the unit ball centered at 0 that is touching some linear subspace along a line segment. So all those points on this line segment will be somehow projections of 0 onto this line linear subspace. But this never happens if things are consistent, right? So if we're in a Hilbert space, then there's always, if we take a closed convex set, there's always a unique point such that this point gives us the infimum of the distance between a given point and points from that set. And again, if you are working in infinite dimensional spaces, you're probably aware of this very famous problem, which can be called, sometimes called Chebyshev set problem, or Klee problem, and so on, is to prove or disprove that if you have a subset of a Hilbert space such that the projection onto that set is unique, which means that this set is Chebyshev, that's the definition of a Chebyshev set. However, the set is not convex. This doesn't work in finite dimensions. In finite dimensions, if you have a set on which the projection is unique, it's a convex set. And also, if you take the closed convex set, then the projection is unique, right? So it's like if and only if. But it's still an open problem in Hilbert spaces. There's examples in some other spaces, but it's a major problem that Still open. Okay, so anyway, I still want to go through projections and just show you a couple of results. So we'll consider only the method of alternating projections. There is an infinity of projection methods that are used very successfully to find points and intersections of convex sets. So basically, either that or a projection method can be used with in a combination with some kind of a gradient method, some kind of optimization technique. But the projection method, what the part of the method that is the projection thing will be doing, is trying to push the algorithm into the intersection of two convex sets. And the usefulness of these methods is in that it can be very easy to compute a projection on some convex set, but it may be difficult to to compute a projection onto intersections of this type of convex set. So for example, a very simple example, if I take the cone of positive semi-definite matrices, right, and an affine subspace or a linear subspace, something like this, right, then it's very easy to compute projections onto linear subspaces. It's very easy to compute projections on the cone of positive semi-definite matrices. You just write down this diagonal decomposition and remove all negative eigenvalues, and that gives you the projection. But computing the projection on the intersection is more difficult. So it's not like semi-definite programmings are usually solved by projection methods, but it's an example of something where that phenomenon happens, right? So projection methods help to find the point in the intersection by combining projections in some way, right? So the very popular method in Australia is Douglas-Rashford, where we don't just project, we reflect, and we do averaging and all sorts of things. There's a lot of methods. So the most basic method is alternating projections. And what we do, we project onto one set. Projection is unique, right? If we're projecting onto convex set, then we project on the other set. In this case, we're already in the set. Maybe the sets are a little flatter, right? So something like this will happen. So we will converge to a point in the intersection of the two convex sets. And in infinite dimensions, there's really interesting things that happen with convergence. So in any case, whether you are in infinite dimensional space, in Hilbert space, or in finite dimensional space, if we take a simple example of two linear subspaces, and so we want to project onto those subspaces, the method will always converge, and also it will converge strongly. I wasn't talking about so far weak and strong convergence, but basically the norm of the difference between the point and the projection onto the set will be going to zero. And the rate of convergence depends on the angle between two subspaces, two linear subspaces. So in finite dimensions, if I have two linear subspaces, I can always calculate the angle between them. If somehow one of them is the subset of the other, the angle will be zero, the cosine of the angle will be 1. If they don't coincide in some sense, then the angle between them will be something, and that something will give me the rate of convergence. Right, so this C here is the cosine of this angle, and I project onto one subspace, the other subspace, one subspace, the other subspace n times, and the distance to the actual projection of the point onto the intersection of subspaces will be bounded by something like this. So it's linear convergence. In finite dimensions, what can happen is that neither of the things is true. So the angle is 0. However, it's not like the subspaces are somehow coinciding. It happens when the sum of the orthogonal complements of these subspaces is closed, is not closed, right? So it can happen that we have two closed linear subspaces, but their sum is not closed. And in that case, the projection method can converge arbitrarily slowly. So no matter what sequence I present, convergence sequence I present, and I can make it somehow converging slow, right? So I can try to make sure that for a very large index, there's some, I don't know, large number, if that makes sense. Yeah, probably not, right? But you can have something that is very fast, converging 1 on 2 to the power n, or something slower, like 1 on n, right? So 1 on n squared. So it doesn't matter what sequence I pick. There will always be some point in a Hilbert space. So if you pick any two linear subspaces for which the angle is 0, there will always be some point for which the convergence is this slow, right? So no matter what sequence I pick, the convergence will correspond to the sequence. And yeah, so, and it's an explicit example. So you generate a sequence, and then there is a starting point that corresponds to the slow convergence. All right, so I should probably stop here because we're running over time. So I'll just leave the slide here because, again, there's a very interesting example of yeah, weak convergence, but let's not maybe look at this. Let's stop here. Right.
Okay, so thank you, Vera, for very interesting talks. So any question from the audience? So please put in the chat box, or you can share, I mean, by unmute and share your videos. So any question?
Maybe I can ask a question. So Vera, you know, at some stage we were working on, say, some kind of extension of convexity, so-called abstract convexity. And I just was wondering, first of all, have you been somehow involved with such kind of project before, or maybe just, you know, I was wondering if there is, in your opinion, especially if you were actually working on abstract convexity at some stage, there is any similarity between abstract convexity and exactly infinite dimensions?
It's a very cool question. I have no idea, but it's a really cool question to think about. I don't know.
Actually, sorry, I didn't hear what yeah, so okay, sorry, may I repeat because I didn't hear what you were answering. So
yeah, I'm just saying that, like, I have no idea, right? So it's a very interesting question, but I have no clue. So of course, right? Yeah, maybe because also I don't work on abstract convexity, right? Yeah. So maybe there is something. Yeah, because you do have convex sets in some sense of some functions or objects that are not convex, but yeah, I don't know.
Yeah, well, separation of two convex sets is also a big question there. So okay, so that's why I thought that maybe you were working on a similar problem. So, but it's not clear if there is any connection here. I guess in mathematics everything is related to each other, but you know, you need to dig very deep.
Yeah, it will be nice to say that abstract convexity is just, it can be placed in the framework of convexity in infinite dimensional spaces, and then you just apply all those results.
That would be great, you know.
Yeah, that would be interesting. Sad also because there's a lot of theory in abstract convexity, but yeah, I have no idea.
Okay, all right, thanks.
So can I have a question? So in the example in L2, a little L2 you gave in the early slides, how does it work if you replace L2 by LP?
In empty intrinsic core?
Yes, empty intrinsic core. Yes, you use L2. Yeah. I mean, like suppose I replaced by LP.
Very good questions.
Is it still true, or it's not true anymore?
So it will still be the same if I replace 2 with any p that I think is larger than 1, because that thing with slowly convergent sequences, that trick works for LP, but I don't remember. I think it works for p greater than all p greater than 1. I'm not entirely sure. Definitely will work for greater than 2. If you have the L1 norm, it may actually not be a counterexample, maybe, intrinsic core will be non-empty, but I'm not sure. So it's a good question. So definitely for a lot of LP spaces, the intrinsic core will be also empty, and it will be exactly for the same reason.
Okay. Okay. Thank you. And another question: when you talk about the projection in the last slide, so your projection is the same as the orthogonal projection, yes?
Yes. So yes. So because so it's an orthogonal projection, but also we think about this as just the closest point, right? So yeah, it's the same thing in the Hilbert space. It's like in the Hilbert space, they are the same thing somehow, right? So the nearest point, yes, it will be an orthogonal projection onto a linear subspace. But I don't know if because you can take also a closed convex set, and you also have a projection, whether the word orthogonal projection applies to this, I'm not sure. Yeah, but in this case, for linear subspace, it is the orthogonal projection. So yeah.
Okay, okay, thank you. So any question from the audience?
Yeah, the problem with LP,
yeah,
with different P, is that when P is not 2, this is not a Hilbert space. And a lot of things change there when you don't have any Hilbert space. In that
become
particular
a Banach space.
Yeah, but not complete. There will not be a Hilbert space.
But do you mean because for the intrinsic core example, we don't need Hilbert space?
No, but yeah, no, we don't need to. But some of the keys of this example will change if you don't have Hilbert space.
Yeah, but you still have a Banach space structure, right?
Yeah, it will be a Banach space, but it's not complete.
No, Banach space is complete by
Sorry,
definition.
Sorry, yeah, you will have a Banach space, but it will not be a Hilbert one.
Yeah, but for this example, it doesn't matter. So
the dual will not coincide with itself.
Yeah, but for this,
okay, so the dual space of LP is LQ.
Exactly.
Yeah, but for this example, it doesn't matter that it's a Hilbert space, right? So still.
Okay.
Yeah, probably not. Yeah.
For this, for projection methods, it's very important that we are in a Hilbert space because, right? Otherwise, we need to assume some kind of strict convexity on some objects that we're dealing with to get unique projections and things like that.
Okay, thank you. I think I've seen the paper by von Neumann, the 1933 paper. It's a very long paper.
You mean about the
the alternating projection theorem?
Okay.
1933. It's a very, very long paper.
Okay.
And the notation is very strange.
Okay, I mean, to be honest, I think that this is so mainstream now in all sorts of works and projection methods that like there's more modern papers, right, to look at those things. And there's also a book by Baruchka and Convex about projection methods. So yeah, we wouldn't be probably looking at Neumann's paper. Although I mean, a lot of things that I was talking about, it's based on joint work with Rainier. So it's not like we produced those things, but we wrote a review paper on intrinsic cores, and we discovered all those very interesting results, rediscovered because for some people they're like known, especially from 1950s. And I think it's great fun. And I have an impression that not everybody somehow knows about this, even people who work in dimensions.
Yeah, but it's very strange. Von Neumann, he knew everything. You know, von Neumann is he knew everything.
Maybe he didn't have as much, in terms of admin duties and teaching.
Anyway, thank you, Vera, for a very nice talk. So, any question for the audience? Okay, if there's no more questions, then thanks, Vera, again.
Thank you.
Okay, we stop the recording here, yeah.